Okay, so in the previous session, we were talking about recursion, and we were talking about the prerequisite conditions for recursion, and solved a couple of problems. And we were on the Fibonacci numbers. So let me open that file. So we were here, Fibonacci numbers, and what we needed was, if I run, let's say, this file right now, then we showed the sequence of calls of how this will be called. So essentially, if we were to draw this, if we were to draw this Fibonacci sequence of, let's say, Fibonacci of 5, or just let's write 5, for example, then this 5, in order to evaluate 5, we will need 4 and 3, Fibonacci of 4 and 3. And in order to evaluate this, we will need Fibonacci of 3 and Fibonacci of 2. And then this will lead to Fibonacci of 2, Fibonacci of 1, then Fibonacci of 1 and Fibonacci of 0. This is Fibonacci of 1 and Fibonacci of 0. Similarly, the tree will expand like this, f1 and f0. And the recursion calls will begin by calling Fibonacci of 4, calling Fibonacci of 5, calling Fibonacci of 4, then this guy calling Fibonacci of 3, Fibonacci of 1. And then once this is evaluated, it will move to Fibonacci of 0. And that's the callback sequence. That's how the calls will work. That's where we ended. The important things I want to talk about, a couple of important things here, is that what is the complexity of this code? What is the time complexity of this code? If you were to notice, on each level here, we are generating two different function calls here, and then this is 2, this is 2. So on each level, we are adding. So for example, here there is one function call, then you have two function call, then you have 2 to the power 2 function calls, then you have 2 to the power 3 function calls. Not literally 3, because we have Fibonacci of 5, so there is nothing here, this is missing. But as you can see, the number of calls are exponentially growing, essentially. This is not a true tree because this has this kind of a structure. So all of these leaves are missing here, but you can see that's kind of a tree. And the height here is Fibonacci of 5, it's decreasing by height by 1. So if we look for Fibonacci of n, then the height here is n for this tree. So you can say, like, an upper bound, this is 2 to the power n. And that's the drawback of some of the recursive functions, that we end up with this kind of a exponential complexity. However, why this exponential complexity is there? Why is it the case that we have this exponential complexity? In terms of in terms of work, if we try to understand what is happening here, is there is a lot of duplicate work going on. So we evaluated f2 here, then we evaluate the whole f2 again, then again. Similarly, if you notice f3 here and then here again. I'm not counting f1 and f0 because they result in base case, But even then, if you notice, they've been called these many number of times. This extra work leads to the exponential complexity. And this gives birth to dynamic programming as well. Later on, when we talk about dynamic programming, this is what dynamic programming solves. It creates a cache in the memory where we store the values of already evaluated items. So we don't evaluate them again. So if we were using dynamic programming, then F2 value would be stored in it. So anytime when F2 is called again, instead of computing F1 and F0 and making these calls, we will just replace it with the value stored for F2. Similarly for F3, we will just replace the value. But dynamics programming is currently beyond the scope. We're talking about recursion. So that's the whole of the Fibonacci numbers that we wanted to talk. Let's talk about some other examples of recursion. All of us have solved string reversing problems. They're not that complicated. They're pretty straightforward. So suppose you have a string, let's say Saturn, then the reverse of that string would be basically be swapping these characters with each other. That will result in the reversing of the string. So you can easily write a while loop and then just keep swapping these numbers. But if I was to ask you how to reverse a string using recursion, okay, recursively reverse string, then how would you do that? If you were to ask you this question, how will this be done? Once again, we go to the basics of recursion, and what we try to do is we first come up with a base case and then a recursive step which goes towards the base case. So if we were to reverse a string, what can be the base case in this case?
Finding the last alphabet in the string.
Exactly. So if you have just one character base string, let's say this, then nothing is to be done. You can just return that character as it is. This is one character. And what is the recursive step here? What can be the recursive step?
Finding the first alpha character from the last.
Finding the first character from the last. You mean to say maybe finding the last character, I guess.
Yes.
Yeah, or you can say that for sure. What can be the recursive step is that suppose if I am going to call a reverse on this, then essentially this is equals to n plus reverse of right. That essentially is the recursive step, and we can keep calling this till we reach the base case. So let me write this down again. Suppose I call my reverse on a string called, let's say, Saturn. Let's take a shorter string, Mars. then I can write this as basically, there are two ways to write this. So essentially you can write it something like this. You can write S plus reverse of mar. So you reduce the size of the string, to one less. And we hope that at some point of time, the length of the string will become one. And in that case, the base case will be there, and then we just return that character. So reverse of Mars will be called, and then that will result in R plus reverse of MA. Then this will be called, and that will result in A plus reverse of M. And at this point, you hit the base case. Once you hit the base case, this function will return M back, because one length string is the reverse of itself. Then this will be A plus M. So this will return as AM here. Then that will be added to R. That will return to RAM. That will return again here. And then S will be added to it with SARM. So you can do that. That's one way of doing it. You can write the recursion in the opposite way as well. That is reverse of Mars. So I took the first character here and then I added the rest of the string. You can just write the opposite as well. You can take this can lead to reverse of Rs plus M. ARS plus M. That also results in the same thing. Then ARS will call this again reverse of RS plus A. Then this will, you get the idea. So given this information, can you write this algorithm now? I have provided the algorithm as well to you. Let me just 6, 14, 2020. What do we have here? Undish star. Undish RF star. Okay. Reverse.py. So we have to write def reverse function, which takes a string and some recursive code. Basically, we have to write some recursive code. And then basically, let's just call reverse of something. Let's say Saturn. Let me paste this in the chat. And you guys can, I'll give you a few minutes. Try this out yourself. So it's going on the general channel. You can take it from there. Any movement forward? Anybody? Okay, let me start here. So, what is the base case here? So, base case is that if the string is of length 1, right, then basically you just return s. If it was a base case is that if the string was of length 1, then you just return s. Else, that is, if the string is not of length 1, then basically uh, we are assuming here that the string is not going to be none, but you can always code for that situation. So you can write in the first line, you can write something like if not s, then basically whatever, return. Okay. But yeah, if len of s is equals to 1, then return s. That's a base condition. Otherwise, what you're going to do is return. Remember what we wrote here? Sorry, where did that go? We can use any of these, but I'm going to use this one. So first character goes to the last, and then we apply the reverse on the rest of the characters. So if this is the string, any string Saturn, then this part of the string can be written as reverse of s of 1 onwards, like that. And then you can write return s of 0. So if the string is of length 1 or more, then it will be this. So if we run now, let's run this code. I'm going a little slow. I'm going a little slow basically so that you guys can.
Himanshu,
Yeah.
you are writing one more function, ref.
My mistake. Sorry. I just reverse of this plus s0. There were multiple problems there. So we are now reversing a string of length 1 less plus adding the first character at the end. So now if we save it and if we run this code now, where are we? Okay. 06, 14. So that's the answer we got by reversing it like that. But let's print it a bit. Let's see how they are being called. These functions are being called. So let's just print. What are we calling it? Reverse of this guy plus this guy dot format. We are printing s of 1 colon and s of 0. Right? Yeah. So if we run this, this is how the functions are being called. We first call the print of a turn plus capital S, and then we print turn plus a, then earn plus t, then you can get the idea. You get the idea. But by printing things in different places, you get the idea of how these recursive calls are being called. So you can just print S here as well and get the understand. First the string was Saturn, then it was A turn, then turn. When the string was Saturn, we called A turn plus S. Then when the string was A turn, we called turn plus A. Then string was turn, we called, and then in the end, this is the answer returned. Any questions here? There's a lot of extra work here as well because we are generating a whole bunch of substrings with this, which is not needed. But I'm giving you the idea of recursion, like how recursion is used. Okay, let's look at one of a classic problem. Okay, I'm going to cover some of the classic problems. There is a problem which is called Tower of Hanoi. I think most of you must have heard of it. If you have not, I'll just quickly explain what this problem is. This is some ancient story or something. I think some books say that it originated in India or something. That basically uh, the puzzle is something like this. You have three poles. You have three poles, and on one pole you have disks arranged in this way that smaller disks are at that disarranged in this way that larger disk is at the bottom and the smaller disk is one above it. So in no situation can you have a situation where there is a smaller disk and then followed by this you have a bigger disk. That is not allowed. Now what you need to do in this situation is, the rules of the game are that you can move one disk at a time from any place. So for example, you can move this small disk and put it here. And then you can move any number of disks anywhere you want, but the only condition is that larger disk cannot be on the top of a smaller disk. And the end goal is that, can you move this whole tower to here? Can you create this whole tower here? If you have not solved this problem ever, then it will be fun. Basically, you can just do this with just three disks. Okay, just suppose you have three disks. One is the radius 1, another is radius 2, and another is radius 3. You can use it with some books or credit cards or whatever you want, phones. But try this. So suppose you have two disks. Okay, and then there are three spots. So if I want to move the whole stack here, then essentially I can move the smaller disk first here, and then I can move the large disk here, and then I can move the smaller disk on top. So I have moved the whole stack of 2 there. And now suppose if I have to move stack of 3. So I'm going to represent this by numbers, 1, 2, 3, like that. Assume. Then how would I do it? I'm going to give you a couple of minutes. You try this out yourself. Any variable to do it? All right, let me show you. Suppose there are 3 disks. Once again, what can you do? You have to move the whole thing here.
You can actually start moving the first over the last task, and then the second also in the last one, and third moves to the second one.
Yeah, exactly. So if you can get to this stage, I mean, think about this. If you can get to this stage where 3 is here and 1 and 2 are here, then you can move 3 here. I've already shown you how to move 2 disks. Then 3 can move here. And then 1 and 2 can move on top of 3. So how can this be done? So suppose that you're in this state, you can move 1 here. Then you have 2, 3 left here. Then you can move 2 here and you have this situation. Then you can move 1 on top of 2. Then you can move 3 here. So this becomes 1, 2, and 3, like that. Then once again, you can move 1 here and 2 here. So this will become this. And then finally move 1 back. But you can notice that there are a whole lot of operations and you can do this. Now, given this situation, and I give you a n disk, then is it possible to move n disks to the other pole? Let's say this is the pole 1, this is the pole 2, and this is the pole 3. And I give you n disks. And the problem arises that how do you move these disks from pole 1 to pole 3? That's the problem. Okay, and I'm going to give you a recursive solution. Just give me a second to this problem. I'm just going to grab a screenshot. Okay, now, so let's work on the recursive solution for this problem. You can solve this iteratively as well, but iterative is going to be now really hard in this particular case. The problem is very hard for an iterative case at this situation. And recursive solution is going to be really easy, but it's hard to come up with the solution in the case of recursion. In the recursive solution, as I mentioned here, you have to think it in this way. First case, what is the base case? The base case is that there is only one disk. There is a tower of just one disk. And in that case, you can just move that disk from one tower, from one pole to another pole. So your whole tower gets moved. That's the base case. What is the recursive step in this case? The recursive step is this, that suppose you have a tower of height n, let's say n. If you can move the tower of height n minus 1, this guy here, if you know how to move the tower of n minus 1 here, on this P2, which is like the intermediate pole, then you can just move the big piece here and move the entire tower on top of it. right? This piece being the biggest piece, you can put anything on it and the condition will not be violated that the bigger disk is under a smaller disk. So that's the base case. So for a tower, so that's the recursive step, sorry. For a tower of n, if you can move n minus 1 to intermediate, and then move the 1 on the top to the final pole, and then move the whole intermediate to the final pole, then that's exactly how we did for 1, 2, 3 as well. So we created a tower of 1, 2 here, then we moved 3 here, and then we moved 1, 2 here. Sorry, 1, 2 here. Because you can use any of the poles, so this pole becomes free once you have moved 3 here, so you can basically rearrange. Let's write this in a recursive way. Okay, I'm gonna call this tower of e.py. Okay, so suppose what I'm going to do is let's call this function move tower. Okay, and I'm gonna fill this later, but let's say the tower move this function has arguments that first it has height of the tower. Okay, what height the tower is. Then it has you have 3 poles here. So suppose you have call start pole, and you have, let's say, destination pole, and suppose you have an intermediate pole. Or you can call it goal, start, goal, and intermediate pole. Suppose those 3 poles we have named. Okay, this one is called, sorry, this one is called start, this one is called goal, and this one is called intermediate for now. So now we are going to write the recursion. So the base condition is that if the tower is of just size 1, then we just move the disk. So, and if it's size 0, then we don't need to do anything. So I'm just going to write if height is greater than equals to 1. Only when the height is greater than equal to 1. Then basically what we can do is move tower of height minus 1. So first what I'm going to do is I'm going to move the tower of height minus 1 from start to intermediate using goal as the buffer. So what I'm going to do is, for example, this is the start, this is the intermediate, and this is the goal. So using this guy as a buffer, I'm going to, this is my source, I'm going to use this as my destination to move the h minus 1 tower here. So I'm going to move 1, 2 here. That's my goal. Then I will move the disk, this guy, to here. So let's just define a function called move disk at the moment. Move underscore disk. Let's say from start to go. And then once the disk has been moved, let's come back here. I'm just gonna, suppose this is your start again of height h. This is the start pole. This is the intermediate pole. And this is the goal pole. So first I'm going to move these h minus 1 disks here. When that has been achieved, then I can move this disk, bigger disk, from here to the goal. And then I can once again move this whole tower again on top of it. So once again move whole tower from intermediate to goal. So I'm just going to write this. So move tower of height -1 again from intermediate to goal using start as a buffer. So I've created a function called move tower, which considers the whole tower and it moves it. Now let's just move disk is nothing. I'm just going to print it. So I'm just going to define move disk as just, let's say you have 2 poles, whatever, you print whatever you want to print. You can here. So suppose you have, how should we print this? Let me think about it quickly. This let's just print the string. Don't worry about anything. Okay. So suppose you have 2 poles. So you have P1. Oh, what happened? Okay. Suppose you have 2 poles, P1 and P2. Essentially, then basically I'm just going to print moving disk from this to this. P1 comma P2. Suppose you just do that. And now, so this program is just going to print stuff essentially, but it will show you the whole move of how it's to be done. So now let's call this function. Okay. Suppose I'm going to call move underscore tower with 3 disks with P1 as the initial pole. Okay. And P1 is the start pole, and then goal pole is P3, and the intermediate pole is, let's say, P2. Okay. Now let's just run this code. Let's see, this runs fine. So now you will see what is happening. So this program is now giving you the exact steps of how to do everything. So for a disk for a tower of size 3, look what it's printing right now. Let's just first of all validate that this is working accurately. I'm going to copy this and let's just validate the steps. So you have these disk of P1, P2, and P3. So moving this from P1 to P3. So first this disk gets moved from here to here. So your tower looks something like this. And the short one here. Then moving disk from P1 to P2. So then this disk moves to here. Then moving disk from P3 to P2. So P3 to P2. So this goes like this. Then moving disk from P1 to P3. So this P1 to P3 that gets moved here. And then you get the idea what it's doing. But essentially the program is able to achieve what we're trying to achieve. I'm going to give you guys an assignment to make this program a little more interesting because I'm just printing and I want you to work with the real numbers as well. But essentially, if you notice, this problem is pretty complicated, but with recursion, you're able to do it in 4 lines. These are the 4 lines. and you are recursively writing a function called move tower, which is moving the entire tower from one location to another. And this is the disk function, which moves one disk at a time. Any questions here? Okay. If no questions, what I'm going to do is I am going to continue some more examples of recursion, but I want to move to the visual aspect of it, to more graphics aspect, so that we see things from a different perspective. In order to do that, I will need to give a quick intro to Python's turtle module. Okay, Python has a graphics module called turtle module. So let me tell you what the turtle module is. So there is a turtle module you can write from turtle import, let's say turtle. Now when you have imported the turtle module, if you call this, what happens is a GUI screen opens like this. And then you can do things here. You can tell turtle some operations and turtle will draw. The idea is that this guy is a turtle with its tail down, and when it moves, it's gonna sketch something. So if I say t dot forward, 100, it will move 100 points to the right. Or I think it's t dot f itself will also work, if I'm not mistaken. No, okay. Or fw maybe. No, okay, whatever. T dot forward, 100, it's gonna move forward like that. And let me increase the width of this turtle so you guys see it more clearly. Then I will begin drawing again. What is this? Pen size, turtle dot width. T dot pen size of, let's say, 10. Let me just try quickly that. Okay, so this is better. Or maybe pen size of 5. Okay. So you can see the turtle. Basically, now I'm going to say t dot backward of, let's say, 500. It will come back to its original location. And then once again, t dot backward 500, t dot forward. This turtle can do a whole lot of things. So now I can see t dot right 90. That means turn the turtle to 90 degrees downwards. And then once again, t dot forward, let's say 500, then it will go here. Then I will say t dot right again, it will turn. And you can see how I'm driving, how I'm designing the whole thing right now. Not only that, it can do things. You can write t dot circle of, let's say, some radius, maybe 200. Then you will notice that it will create a circle of radius 200 like that. In fact, I can just create very beautiful shapes. Like I can just say for x in range, let's say from whatever 10 to 200 in the increments of, let's say, 10, t dot circle of 10. Suppose I do that. X, sorry. When I do that, notice how printing those circles right now. It's incrementing in the width of 10, and it's printing those circles there till 200. But you got the point. So there is a turtle module which does the graphics. Now I want to show you something. So for example, just like in this example, we are printing these circles. I want to draw some complicated shapes using recursion. Okay. And what I'm going to do is I'm going to write a program for that. So the first program I'm going to do is called a spiral.
Himanshu, sorry.
Yes.
So if I like need to practice this one, like where, how to do that, like how that graph will come.
So basically, you have Python ready for in your system?
Yeah.
So basically what you write is, fire up the Python terminal and you write from turtle import turtle, or import everything, something like this. You can write whatever.
Okay.
Okay. Now then you initialize a turtle object by writing any object name. You can write my turtle or something. You can write t1 equals to turtle, like that, with the capital T. This will start the window for you.
Okay.
And then you can try all the operations there. It's pretty easy.
We can run from ID as well, right? From PyCharm also we can do that, right?
Yeah, you can run it from PyCharm as well. That's right.
Okay.
So with PyCharm, there'll be a trick. Let me find that trick. Just give me a second. Actually, let me write the code directly in a file, and then you can follow, or I can post that code, and then basically I'll check. So let's just draw some interesting shapes, okay, using recursion. Suppose I want to draw a spiral. Okay. Suppose that I want to draw a spiral figure. So spiral is something like this. Consider this to be a square spiral. That it is something like this. Okay, so basically it's a square which is getting spiraled into a center, and then it's stopping at some point. Okay, I know that turtle has a forward command to move forward, and then turtle has a right and a left command which turns the angle of the turtle. So this is the turtle. If you say right, then it will move right by whatever degrees you want. If you put 90 degrees, then it's going to turn right angles. This is all the information I need to move forward in this particular example. So what can I do? So I can say to turtle to move forward by some distance. Suppose the initial length of the spiral is, let's say, whatever x. Then I can tell turtle to move forward x. Then I can tell turtle to turn right by 90 here. Then I can say turtle to move forward by, let's say, x minus some small distance. So what that will do is that will create the spiral. It will, each time the side will be slightly smaller, and we'll move towards the spiral. And then I can move again righty. Then I can once again say f of x minus a little bit more, 2 delta. So it becomes slightly smaller. And then just continue till whatever this x minus x, we reach this situation. And it becomes 0. So I'm going to write this recursively, okay? And I'll tell you the book where I'm taking this example from, so you guys can also follow that book. I talked about it in the last class as well, but I'm going to paste it on the Discord channel. So let's take this, Okay, I'm gonna call this vim spiral.py. So first thing is I'm gonna say from turtle import turtle. So now whoever was using PyCharm, now this you can, whatever I'm going to do will work on PyCharm. But I'm going to post this code as well, so you don't have to copy and paste. Now I'm going to initialize a turtle. T equals to turtle. And now I have to write one command here, which is a variable, any variable it can be. I'm just going to create a window and I have to write this t.getScreen. That's the only thing. Now I'm going to write my spiral. Def spiral of, let's say, initial width is width. Okay. And let's pass the turtle variable to it as well. Well, it's a global variable, so it's okay. We don't have to pass it. So def spiral width. Okay, now I'm just going to write if width is greater than 0. So that will ensure that base case has reached, which is when the width is 0, don't do anything. If width is 0, then basically t dot forward width, this direction, and then t dot right 90 degrees. Now recursively call the spiral with width of, let's say, minus 10. And that's it, right? Basically, I'm just writing, this is the base condition, which is saying that essentially that only this will only work when the width is greater than 0. And I'm reducing the width towards 0 by the step of 10 here. So on each time I'm saying move forward with the width. Okay, I need to move this to here as well. I'm saying move forward with to this width, then turn right, then again call spiral with width of minus 10. Okay, let's run this code. Spiral of, let's say, 200. And I'm also going to set some pen size here. Let's just, because otherwise it becomes hard. T dot pen size of, let's say, 5. Spiral of 200. Okay, let's run this code now. Sorry, exit Python 3 spiral.py. Let's see. So now you see it's going to print that kind of a spiral. And it stopped because I did not, it killed the window itself. Let me add one more command here, which will be t dot something like, no, sorry, window. That's why I created the window. Window dot exit on click. And I'm going to do a bit more here. Instead of this, let's call it 500. Okay, and run this code again. Now you will see that it's going to print a spiral of this form. This is a square spiral. We can also print a circular spiral if we get a little tricky. But essentially, you're able to achieve this graphics by using a 2-line of code and one function, one recursive call. And that's your spiral printed. And I'm going to, the last line that I added in my piece of code, which is this, I created a window like this. So I'm not fully familiar with the turtle. So I just use some of the commands that I know. Exit on click. Basically, if I touch this window now, my window will exit. Where did it go? There. If I touch it, then the program will exit. Okay, so we are over time. I'm going to stop the session and we're going to pick up from here in the next session. If you have any question, feel free to post it on the Discord.